All right, let me take the attendance first. Kirsten, Sam,
Here.
Patrick,
Here.
Kyler,
Here.
Ben Conkin,
Here.
Gabe,
Here.
Dylan,
Here.
Adam, Ginny, Austin, Hunter, Jeffrey, Hunter was here. Okay. Max,
Here.
Kevin, Derek, no? Nick,
Here.
Landry,
Here.
Michael,
Here.
Kaylee, Sophie, Molly, Ryan,
Here.
Seth,
Here.
Joe,
Here.
Zach,
Here.
Hayden,
Here.
Alex,
Here.
Erica, Tiffany, Yusuki,
Here.
Nicole, Nick Hess. Do you have a brother who went here? Who came here? I had a student whose last name was Hess as well.
You may or may not be related.
Yes. Okay. So, how was your first 2 days? Kind of boring. Yeah. Yeah, it's going to become exciting, and then it might become again boring at the end. Okay, so what I want to do is start with reviewing some stuff. And like I said, you should start reviewing yourself from the review attachments that I sent, because I might not be able to go over all the review topics that I gave you in those attachments. So what I'm going to do is, first of all, start by reviewing real numbers. So the first topic is we're going to go over some basic information on real numbers. We are going to use the following notations. If I write an n like this, this denotes the set of positive integers. So it denotes the set of positive integers 1, 2, 3, 4, ... So this is the set of positive integers. The next bigger set of numbers would be denoted by z with a double line here in the middle, and this will denote the set of all integers. So you have the positive integers, negative integers together with 0. So you got -2, -1, 0, 1, 2, 3, ... So this is the set of integers. Set of integers. The next bigger set of numbers will be denoted by Q with a line, and this will denote the collection of all rational numbers. So these are numbers which are ratios of integers. So A over B, where A and B are both integers and B is not 0. Of course, it cannot be 0 because it's in the denominator, right? The symbol that I have here, this symbol here, that symbol means belongs to. This symbol means belongs to, or you can say contained in. So these are basically this symbol says A, B belongs to the set of integers. Is everybody clear? Okay. So that these are our rational numbers. Okay. Rational numbers. Okay, so these are for a long time in human history, people thought those are the only numbers. Okay, so the Greek philosophers, you know the name Pythagoras, right? So let's imagine that during that era, there are lots of people probably didn't have much to do in life, didn't have very many friends, so they used to go into caves and work on silly problems. So let's say one such guy is because he knows the Pythagoras Theorem. Let's say you have a right triangle, and this side has length 1, this side has length 1 as well, and let's denote the length of the other side, the hypotenuse, by x. So what can we say about x? What can we say about x? So by Pythagoras' theorem, yes, so what we could say is that x squared is the square of one side plus the square of the other side, right? And so that means x squared is equal to 2. And the Greek philosophers were very, very confused about it, because for them at that time the only numbers were the rational numbers. What they found out is that whatever this x is, whatever that x is not a rational number. Okay, so x is not a rational number. That is, they can justify that you cannot express x as the ratio of two integers. Okay, there is no way of expressing x as a ratio of two integers. So it's not a rational number. And there is a proof of it, but I won't give you the proof. So they were confused because they thought the only numbers are the rational numbers. So they were so afraid that for a long time, they wouldn't call x a number. They would call x a length. Okay, so they will differentiate between lengths and numbers. Numbers are just rational numbers, and numbers like x were lengths. Okay, so nowadays, what do we call x? As somebody said, we say that x is root of 2. Okay, we denote the number x. We denote the number x by the symbol root 2. Right. And so what we are saying here is that root 2 is not a rational number. So the point is there are lots of numbers which are not rational numbers. Can someone give me other examples of rational numbers? Sorry, irrational numbers. Pi. Pi appears, you have seen this all your life in many courses, physics, math, area of a circle, right? That's the First place you see pi. Any other? E. Yes. And root 5. Let's just be in real numbers. Okay. So root 5 and others. Okay. So ... These are irrational numbers. What are real numbers? The real numbers, we will denote that by this symbol. So it will be R with an extra line on the left and then another line here. So this symbol here represents the real numbers. And what are real numbers? Well, you put together the rational numbers and the irrational numbers. So you put together the collection of rational numbers and irrational numbers into one collection, and that's the set of real numbers. So this is the set of real numbers. Now, one thing you want to notice is that the set of positive integers are inside of the integers, right? So that is, if I look at the set of positive integers n, it is included inside of the integers. So this symbol here that I have, this symbol here means contained in, okay? Contained in. And of course then z is inside of q, right? Because any integer can be thought of, if I have the integer -2, you can write it as -2 divided by 1, right? So it's a rational number. And all the rationals are included inside of the real numbers. Is that clear? Everybody's okay with that? Now, one question is, how many real numbers are there? How many real numbers are there? And to answer that, we are going to use the number line. And the number line, so here's the number line. The real number line. And what is the real number line? Well, the real number line is an array which extends to infinity on both sides. Okay? And we pick a point arbitrarily and call it 0. So 0 is denoted by that point. And then we pick a unique length. Okay? And whatever our unique length we pick, so let's say this much is a unique length. So the number 1 would be represented by this point. The number 2 will be represented by this point here. The number 3 will be represented by this point. Negative integers will be on the other side of 0, and so on. Right? And which point will represent half? Well, the number, of course, in between here, right? That's going to represent half, right? The point here will represent what? Right in the middle? 3/4? And so on. So all the rational numbers will be represented by some point there. The point is, every point on this line represents a real number. And every real number can be represented by a point on this line. Which is to say that there is a one-to-one correspondence between the points on the line and the set of real numbers. Is that clear? And so how many real numbers are there? Well, as many points you have on the line. Okay? So there is a 1-to-1 correspondence between the points on the number line and the elements of R. Is everybody okay so far? Okay. Decimal expansions. We express numbers by using decimal notations, right? 2.5, right, represents the number what? 5/2, right? 5/2. So, what are the properties of decimal expansions of rational numbers? So here's the remark. The decimal expansion of a rational number is either terminating or repeating, right? And how about the decimal expansions of irrational numbers? The decimal expansion of an irrational number is neither. What I mean is it's neither terminating nor repeating. Okay? For example, let's say I have the number 3.25. So this is a terminating decimal expansion, right? You have only finitely many digits. This can be expressed as the ratio of two integers. What is that? I can write it as the ratio of which two integers? Same as 325 over 10? 100. 3.25 is the same as 325 over 100, right? So if you have a terminating expansion, that's easy to see why that's the ratio of two integers, okay? How about something repeating? Let's say I have the number, let's say I have a repeating decimal expansion, let's say 4.17, and this symbol means that this number is 4.17171717, and you if you keep saying that, you will probably fall asleep. We want to see why this is a ratio of two integers, right? Why is this a ratio of two integers? How do I see that? Anyone knows? Well, I am going to let capital M denote this number. Okay, so 4.17171717. So m, let's say m denotes that number. I am going to multiply both sides by 100. Why 100? Because I have how many digits are repeating after the decimal point? 2. So I multiply by 100. If I have 3, I multiply by 1,000. So if I multiply both sides by 100, could you tell me what do I get? 417.171717. Right? Okay. Here's my question for you now. Is if I subtract if I subtract m from 100m, what do I get? 99m. Okay. So I subtracted on the left. What happens when I subtract on the right? What do I get? Is that 413? You agree with that? Notice that after the decimal point, I have the same digits, right? So when you subtract, all the digits after the decimal point cancels out. So you are basically subtracting 417 minus 4, which is 413. So you get 413. Well, you have 99m here and 413. So what is m? What is m? 413 divided by 99. Is that a ratio of integers? Sure. So I can see that the number m that we started with is indeed a ratio of integers, so it is a rational number. So if you have a repeating decimal expansion, it is a rational number. Now, decimal expansions of irrational numbers, not terminating and not repeating as well, because you cannot express them as a ratio of two integers. So if you search for the number pi on Google, you'll see there are many places where they give you thousands of digits of pi. Okay, and by knowing the very last digit that you computed, you wouldn't be able to tell me what's the next one coming until you compute it. Okay, so there is no pattern, there is no repeating pattern when you look at pi, and you see all these people on YouTube or TV. Sometimes they say that, well, I have memorized the first 500 digits of pi and things like that, right? And of course, how about your first assignment is memorize the 500 digits of pi? No? Okay, I didn't think so either. Okay, so I don't know that either, and I'm not going to try either. Okay, so what I want to, so these are the real numbers. You have seen the decimal expansions, how they look like for rationals and irrational numbers. What I want to do next is recall the interval notations, and I'm pretty sure all of you have seen those. So the next topic would be interval notations. Okay, so let me start with the open interval a to b. What does this represent? Well, it's a set of real numbers. Okay, and what set of real numbers? Well, Anyone remembers what set of real numbers is represented by this interval? Yeah, all the numbers between a and b, excluding a and b. So I should write it this way, right? All the numbers x inside of the real numbers, set of real numbers, such that x is larger than a, less than b. So that's the set of numbers represented by this symbol. In terms of the number line, what this means is that if I have this representing the number a, this point representing the number b, then the points in between a and b represents the set from a, the open interval from a to b. But of course, we have to exclude a and b, right? We have to exclude a and b. Okay, so what are other interval notations? How about closed at A and open at B? What does this represent? What's the difference? Now we include A. So this is all the real numbers x inside of R, such that A is less than or equal to x is less than b. I should have said I am assuming that b is bigger than a. Okay, probably I should have said that at the beginning, that a, b are real numbers and a is less than or equal to b. So b is the bigger number. Okay, and I'm not going to sketch this. The other one would be, you might have open at A, closed at B. So what do we change in the inequalities? We just switch them, right? Okay. So I won't write it down. You can fill that in. And we might also have closed interval, closed on both ends. And in this case, what's going to happen? We include both A and B as well, right? We include both A and B. What else am I missing? What other types of intervals am I missing? Any other types of intervals? Yeah, how about closed at A and then up to infinity, and this guy represents all the real numbers x, such that x is what? Greater than A. So all the numbers greater than A are in this set. I can also have open at A. I made a mistake here, didn't I? Should be greater than or equal to, because I have to include A. For the second one, though, I don't have to include A, right? The second one, everything bigger than A but not A. Or I could also have negative infinity to B, right? Which would be all real numbers x, such that x is less than or equal to b, right? And then I also have negative infinity to b, open at b. So the second one does not include b, right? Any other intervals that I'm missing? Negative infinity to infinity, which is what? Negative infinity to infinity, which is just all real numbers. Okay? Everybody is okay with that? Okay. So those are our interval notations. Any questions so far? Okay. What I want to write down are the arithmetic properties of real numbers. So the arithmetic properties of real numbers. Well, the real numbers, real numbers comes with two operations, right? Addition and multiplication. I'm going to denote multiplication by a dot, right? You can add and multiply numbers. And what are their properties? Well, number one, addition and multiplication, they are both commutative. What does that mean? It means that, for example, what it means is that 1 plus 2 is the same as 2 plus 1. 3 times 5 is the same as 5 times 3. Right? Number 2, they are both associative. Again, what does that mean? It means that if I am adding 2 plus 3 plus 5, okay, I can either add the first two numbers and then add the third one to the result, or I can add the second two numbers and add the result to the first one. And similarly for multiplication, 2 times 3 times 5, that's the same as 2 times 3 times 5. Okay? So that's what we mean by associative property. Property number 3, addition is distributive over multiplication. So what does that mean? It means that if I am multiplying 2 times 3 plus 5, I can write 2 times 3 plus 2 times 5. Okay? So you can distribute 2 over the addition. So we say that, I should say differently, sorry. I should say multiplication is distributive over addition. Okay? So this is known as the distributive law. Some more examples that you have seen in algebra are like this. You have used them always, I guess. If you're multiplying 2x plus 1 with 3x minus 5, what do you get? Well, you use the distributive law to multiply them, right? There are other, let me just first show how you can use the distributive law. That is, I can say that this is the same as 2x plus 1 multiplied by 3x minus 2x plus 1 multiplied by 5. Okay, and then now I can multiply them. I get what? 6x squared plus 3x minus 10x plus 5. And what is that? 6x squared minus 7x plus 5. Of course, usually you might be multiplying this way, right? You might be multiplying these two first, and then these two for a second. You might be multiplying these two next, and these two, right? Yeah.
Should be minus 5.
Where is minus? Oh, hey, this should be minus 5. Thank you. This thing here should be minus 5. Okay. Everybody's okay? So you used what you called FOIL, right, to multiply them? So that's what we did. Okay, so that's how distributive law works. Any questions so far? Anyone has any questions? I don't want to give any more lecture right now because this is where I ended in the morning section. However, if you have any general questions about the course or anything else, you may ask now. Okay, remember, I think did I go over time last time? Yes. Or I am giving you back your time. So just to let you know, we are even now. Actually, I gave you some interest too. So I'll see you on tomorrow. Remember, it's 1:30, not 2.